Hello class, this is a video tutorial on the fundamental counting principle. Let's consider the two following scenarios. In the first one we have this person named Adrian, and he owns 3 shirts and 4 pants. For how many days can Adrian leave the house and have a unique arrangement of clothes worn? So for example, on one day he might decide to wear one of his shirts, so shirt 1, and pair it with one of his pants, shirt 1, pants 1. On a different day, he could wear shirt 1 again and pants 2 this time. This arrangement is unique to the first one. So that's 2, shirt 1 and pants 3. That's a third one, shirt 1 and pants 4. So here we have 4 different arrangements using shirt 1. Another one we can do is shirt 2, pants 1. And I'm sure you're starting to see a pattern in this. Shirt 2, pants 2, shirt 2, pants 3, shirt 2, and pants 4. And that's 8. And I'm sure if we continue this with a third set, I'm sure we would have gotten this one here. So in this we can count that how many unique arrangements, or how many days can Adrian leave the house with a unique arrangement of clothes. From here we can see 12. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We could have also have done this using a two-way table like this, where we organize all the pants along the top, all the shirts along the side. We can order them out here, so 1, 1, 1, 2, and so on. I want you to pause the video and give this a go yourself. And here we have now Beth. Beth is a picky eater and never wants to have the same exact arrangement of entree, main, and dessert. How many times can Beth visit a restaurant that offers 4 entrees, 3 mains, and 2 desserts before she has a repeated experience? It's essentially the same concept with this in a different scenario. So here are the 4 entrees, the 3 mains, and the 2 desserts. This one's a little trickier. So we could have the first entree, the first main, and the first dessert. That's one set. In a different day, she could have the first entree, the first main, and the second dessert. That's unique because the arrangement of this is different to each other. This one here, we can have E1, M2 this time, and then D1. Notice how we're changing them very systemically. I'm obviously not going to do the rest. Here's the remainder for entree 1. And if we were bothered enough, we could finish off the rest for entree 2 and repeat the exact same thing for entree 3. So in this case, if we had to count them, that's 1, 2, 3, 4, 5, 6. 6. That's lots of 1, 2, 3. 6 times 3, we could have gotten 18. Was that right? Am I missing some? We don't know actually exactly how many there are. It's actually getting really large, a very large amount that we'd have to count. Like, I mean, if we did this using a probability tree, we could have done it like so: entree 1, entree 2, and entree 3, and then branch from there. M1, M2, M3, and for each of these we could further branch it to dessert 1 and dessert 2. Okay, so we could have modeled this using a probability tree as well. Now, for smaller scenarios, and I would deem these to be smaller, in this case we had 12, and this one was already starting to get a little bit too large to count manually. Modeling the problem with letters and counting each arrangement, as I've shown you here, it's kind of useful if it's a small amount. But with large scenarios, we should apply the fundamental counting principle. What this states is, let event P can occur P number of ways, and event Q can occur Q number of ways, and P and Q are independent of each other. So if this is the case, the total number of unique arrangements the events can occur is P times Q. And this can be extended to any number of unique events. So, going back to this one, we have one set of events is picking out a shirt, and it can occur 3 times. The other event is picking out a pair of pants, which can occur four different ways. So in total, we could have easily found the total number of unique ways as 3 times 4 is 12. For this one, the 3 different events we can see is picking out an entree, picking out a main, and picking out a dessert. And each of them could occur 4, 3, and 2 times. And for the total, we could find it by doing the following. 4 times 3 times 2. That's 8 times 3. That's 24 total different ways we could have organized these to be unique. Now let's do a few examples. So that's the general idea of the fundamental counting principle. It's that if we have unique events and each event can happen a certain number of ways, the total number of ways we could combine them is just the multiplication of each individual. So let's do this as an example. So how many 4-digit PIN codes are possible? Well, if you think about this, the first event is the first digit. First digit. The second event, well, that's the second digit. And so on. Third digit and fourth digit. In this first event, how many different things or objects, we're going to call them, how many different objects can go into the first digit? Well, the numbers system that we have the digits that range from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you are saying, what about 10? 10 is a combination of 0 and 1. So it's not a single digit. So in total, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways that the first digit could be selected. So that's 10 for the first event. Well, I'm pretty sure you can see that for each and every single event in this example, it can occur 10 times for the second digit, 10 times for the third digit, and 10 times for the fourth digit. And the total number of ways that we could do this is just by multiplying them like so. That's 10 to the power of 4, which I believe is 10,000 different. There are 10,000 different 4-digit PIN codes. A thief has 3 guesses before a card is locked out. What's the probability that they could guess correctly? Well, if there's 3 possible ways that they can guess, out of a total of 10,000. And it's as simple as that. Probability is equal to 3 over 10,000. So I hope that gave you an insight into the fundamental counting principle. And hope to see you in the next video. Best of luck.